Welcome in the series of lectures of sequence of real numbers. So this is the fourth lecture. In last three lecture, we have to study the what is the sequence, what is the convergence of sequence, what it is monotonically increasing and decreasing sequence, bounded above sequence and bounded below sequence. So we are taking one more example here. So what is the example? So example, if Sn is equal to 1 upon 3 plus 1 plus 1 upon 3 square plus 1 and so on, 1 upon 3 raised to n plus 1. Okay? Then show that the sequence Sn is convergent. So show that this sequence is convergent here. So what is the solution? Let us consider the sequence. Let Sn is equal to, so n the term of the sequence. So 1 upon 3 plus 1, 1 upon 3 square plus 1, and n the term of this n the term 3 raised to n plus 1. So this is the nth term of this sequence that is given here. Okay, so we find here what is Sn plus 1. So Sn plus 1 is, there are n terms in this Sn plus 1. So that is 1 upon 3 plus 1, 1 upon 3 plus 1, plus 1 upon 3 square, plus 1, plus and so on, 1 upon 3 raised to n plus 1, plus 1 upon 3 raised to n plus 1, plus 1. Okay? So this is Sn plus 1. One more addition term. This is the addition term in Sn plus 1. Okay? So now, so Sn plus 1 minus Sn is equal to, so this minus this, this minus this. So what will you get? So this term, those terms get cancelled. So the remaining term is only 1 upon 3 raised to n plus 1 plus 1. Okay? So this is greater than 0 always. This is a positive. So this is greater than 0. So therefore Sn plus 1 minus Sn greater than 0. So we get here, therefore Sn plus 1 greater than Sn for all n is equal to 1, 2 and so on for all. So that is for all n. So that is 1, 2, 3, 4 and so on. So what it implies? Sn plus 1 greater than Sn. So it implies, so this is the definition of increasing sequence. So this is a definition of increasing sequence. So therefore, this sequence Sn is increasing, means non-decreasing, increasing sequence. Increasing sequence. So this is the first part of the solution. So moreover, what is the second part? Moreover, so what is Sn? Again we take Sn is equal to 1 upon 3 plus 1 plus 1 upon 3 square plus 1 plus and so on 1 upon 3 raised to n plus 1. Okay? Okay. But this is less than. So Sn is less than. Yes, so Sn is less than 1 upon 3 plus, because this is 1 upon 4, less than 1 upon 3. So this is less than 1 upon 3 square and so on 1 upon 3 raised to n. 3 raised to n means this is less than this. So Sn is less than this. So this equal to, we common out 1 by 3. We common out 1 by 3. So into bracket 1 plus 1/3 plus and so on 1 upon 3 raised to n minus 1 after taking common out 1/3. Okay, so there are n terms. But this is a geometric series. So 1 plus 1/3 plus and so on 1 upon 3 raised to n minus 1. There are n terms and this is a geometric series. So we know what is the sum of that geometric series. So first term is 1 and the common ratio is 1 by 3. So the sum is 1 minus common ratio. So what is common ratio? 1/3 raised to n. So that is 1 upon 3 raised to n divided by, means 1 minus r raised to n. R is 1 by 3 common ratio divided by 1 minus r. So that is 1 minus 1 upon 3. So this is equal to 1/3. So what is this? 1/3, 2/3. So 1 minus 1 upon 3 raised to n divided by 2/3. 2/3. Okay, 1 minus 1 by 3. So 3 get cancelled. So this is what here? So this is 1/2. 1/3 get cancelled. 1 minus 1 upon 3 raised to n. Okay? Okay, so therefore, but what is this? So this is less than 1. 1 minus something. So this is less than 1. Therefore, this term is less than half. Okay? Because this is less than 1. Therefore, Sn is less than 1/2. Less than 1/2. So this is upper bound. We say m. Okay? And if all for all n. So if Sn is less than 1/2 for all values of n, means all terms of that sequence less than 1/2. And 1/2 is upper bound. Therefore, this sequence Sn is bounded above. Therefore, this sequence Sn is bounded above. Bounded above. Okay? And we know the theorem. If the sequence Sn is increasing sequence and bounded above, if the sequence Sn is increasing sequence and bounded above, therefore the sequence Sn is convergent by using theorem. Yesterday we proved this theorem, and by using that theorem the given sequence is convergent. Okay? So this is a very simple example. We take another same type of example. Let us take an example here. Let us take an example. show that show that show that the sequence Sn show that the sequence Sn where Sn is equal to n upon 2 raised to n is convergent. So this is one more simple example we have taken here. So what is the solution of that example? Solution, let given that let Sn is equal to n upon 2 raised to n. n upon 2 raised to n. So what is Sn plus 1? So Sn plus 1, put n is equal to n plus 1. So that is n plus 1 divided by 2 raised to n plus 1. Okay? Then Sn plus 1 minus Sn is equal to n plus 1 divided by 2 raised to n plus 1 minus this n upon 2 raised to n. So this equal to what? So that is n plus 1 divided by 2 raised to n plus 1 means 2 into 2 raised to n minus n upon 2 raised to n. 2 raised to n. Okay? Then taking LCM of this. So LCM is this 2 raised to n plus 1. Then what happen here? So that is n plus 1 minus multiplying by 2 here. So that is 2n divided by 2 raised to n plus 1. So we get here. So n, what happened here? 1 minus n minus 2n minus n divided by 2 raised to n plus 1. 2 raised to n plus 1. Okay. So what is this? So this is always greater than 0 for all n. Always greater than 0. Why? Put something n is equal to something n is equal to 1. So n means all natural values here. So n is equal to 1. So we get 1 minus 1, 0. Put n is equal to 2. 1 minus 2 minus 1. So we get negative terms here. So this is less than equal to 0. Therefore Sn plus 1. Sn plus 1 minus Sn is less than equal to 0. So this implies that Sn plus 1 less than equal to Sn for all n. So this is the definition of what? This is the definition of decreasing sequence, non-increasing sequence. Therefore, the sequence Sn is what? Decreasing sequence. Is decreasing sequence. Okay. So this is the first part of the solution here. So now we take next part. So that is show that the sequence is bounded below. Moreover, okay. So Sn is what here? Sn is equal to what? N upon 2 raised to n. N upon 2 raised to n. Okay. So this is always greater than 0, no doubt. Why? For all n. Why? Because n is equal to 1, to put n is equal to 1, we get positive value greater than 0. Okay. n2. So Sn is greater than 0. So this is we say here. So this is small m. Small m means this is a lower bound. Greatest lower bound here. So all terms of that sequence greater than 0. So 0 is the lower bound. Okay, and this is a definition of bounded below sequence. Therefore, this sequence Sn is a bounded below sequence. Bounded below sequence. Okay, below sequence. Then by theorem. What is the theorem? What is the theorem? A decreasing sequence, Sn is a decreasing sequence, and which is bounded below, then the sequence is convergent. Okay, therefore by using theorem, the sequence is decreasing as well as bounded below, therefore sequence Sn is convergent sequence, hence the example. So very simple examples. Okay, so these are the examples here. You can solve the examples. तुम्ही या ठिकाणी एक्झाम्पल सोडवू शकता. मी एक्झाम्पल्स देणारच आहे फॉर होमवर्क. त्यात तुम्ही एक्झाम्पल सोडवू शकता. So now we go ahead. We are taking here the operations of convergent sequences. So what is the operations of operations on convergent sequences? So we take here theorem. So what are theorem? What is the theorem here? Okay. So if Sn n is equal to 1 to infinity, you write this, or not simply write a Sn only, and Tn Sn and Tn. Okay, B2 sequences are sequences of real numbers sequences of real numbers. So those sequences are convergent sequence, that is given here. So if that is limit of Sn as n tends to infinity is equal to L and limit of Tn. So this is also convergent sequence. So having limit some m, that is given here. Then show that. Then show that limit of Sn plus Tn as n tends to infinity is equal to L plus n. So that is proving here. Means what? So this is a convergent sequence having limit L. This is a convergent sequence having limit m. So simply we say that the sequence Sn plus, so this is algebra of the sequence. So operation means plus operation, minus operation, multiplication operation. Okay, division operation. So then adding, so this is also sequence, adding Sn plus Tn. Then show that, what is the meaning of that? Then show that this is a convergent sequence having limit L plus m. Okay, proof is very simple here. So what is the proof? So what is the given that here? So since sequences are convergent, so that is the limit of Sn as n tends to infinity is equal to L, and limit of Tn as n tends to infinity is equal to m. Then what is the definition? Then for what is the epsilon definition? Then for epsilon positive, there exists n1, n2, such that what? So what is the definition of convergence of sequence? So that is what is the definition of limit. So what is the definition? We already learned the definition of limit. Yeah. So for given epsilon positive, there exists n1 and n2. So n1 for this, n2 for this. So by definition, so mod of Sn minus L less than epsilon by 2, where n is greater than n1 equal to n1. Okay. So for the convergence of this, we write definition. Okay. So what is the definition of that limit? Similarly, Sn minus m less than epsilon by 2, where n is greater than equal to n2. हे अगोदर झालेलं आहे. या दोन डेफिनेशन्स आहेत याच्या आणि याच्या. So we say this is equation number 1. So equation number 2. Okay, let n is equal to maximum of, let us consider, let us take m is equal to maximum of n1 and n2. यातला जो कोण मोठा असेल त्याला आपण we say that is n. Consider mod of Sn plus Tn minus L plus m minus L plus m. So this can be right as it is here, Sn minus L plus Tn minus m, Tn minus m. So what? So by using inequality, so you know inequality a plus b is less than equal to mod a plus mod b. We know that this inequality by using that inequality. So this is less than equal to mod of Sn minus L plus mod of Tn minus m. Okay. But what happened here? But Sn minus mod of Sn minus L less than epsilon by 2. आता तुम्ही इथे epsilon by 2 घेऊ शकता, काय प्रॉब्लेम नाही आहे. कारण का पूर्वी डेफिनेशन मध्ये एप्सिलॉन घेतलं होते, इथे epsilon by 2 घेतलं म्हणजे काय बिघडलं? कारण का epsilon इज हवे स्मॉल, तुम्ही डिवाइड 2 ने केला तर आणि लहान होईल, काही हरकत नाही आहे. ओके. सो दिस इज लेस दॅन बाय युजिंग दिस. सो दिस इज लेस दॅन epsilon by 2 plus so epsilon by 2. So this is epsilon. This is epsilon. Okay. So therefore Sn plus Tn minus L plus m is less than epsilon, where n is greater than equal to capital N, because capital N is the maximum of n1 and n2. So what is the maximum of n1 and n2? So that is n here. So we take n1 for that and n2 for that. Then we take n because of n is the maximum of n1 and n2. So we write this limit as n tends to infinity of Sn plus Tn is equal to, by definition, upper limit, so L plus m. So hence we prove this. Okay. So this is the algebra of the sequence here. So we say that here, by using this, we say that here, if Sn is converges to L, Tn is converges to m, then Sn sequence Sn plus Tn converges to L plus m. So this is a very simple proof here. So now we take next theorem. So this is we say here this is theorem 1. What is the theorem 2 here? So same theorem like that. If Sn and Tn are convergent sequence of real numbers. So just we take theorem 2 here. What is the theorem 2? Theorem 2. So what is the theorem 2? If Sn and Tn are sequences of real numbers, and if limit of Sn is L and limit of Tn is M, so that is given, then prove that Sn minus Tn is equal to L minus M. So L minus M. Okay. So theorem 2 is what? Sn and Tn are sequences of real numbers, and if limit of this is L and limit of this is M, then prove that limit of Sn minus Tn as n tends to infinity is equal to L minus M. Means that sequence, malachi plus sign होते का minus sign. So that sequence is converges to L minus M. So that is the theorem 2. And you prove that theorem. कारण का you करू शकता. मागे कसं तुम्ही केला त्याच इथं रिपीट करायचं काही कारण नाही आहे. So very proof is very simple. You prove that theorem here. Okay. So next, what is the theorem 2? 3. Theorem 3. Okay. Okay. If Sn is a sequence of real number and if C is any element of R, so C is a constant, so R is a set of real numbers, and if limit of, so Sn is a convergent sequence, so having limit of Sn is L, okay, then what happened here? So multiplying C, that is a constant, to each element of that sequence. So C into S1, C into S2, C into S3 and so on. Then what is the limit of that sequence? So we multiply by C to each element of that sequence. So S1, S2, S3 are Sn are the elements. So multiply by C. So that is CS1, CS2, CS3 are the element of that sequence. And if this sequence is converges to L, therefore the sequence CSN converges to CL, C into L. Okay? त्यामुळे काही कॉन्व्हर्जन्सचा फरक पडत नाही. प्रत्येक एलिमेंटला C न गुणलं आणि त्याचं लिमिट काढलं तर काही पहिल्याच गेला C into L. So proof is very easy. Okay? तर मी या ठिकाणी थांबतोय. उद्या मी पुन्हा एक्झाम्पल्स घेणार आहे. तत्पूर्वी तुम्ही मला एक सगळ्यांना विनंती आहे, कारण का आपली या ठिकाणी BSc टू शिवाजी युनिव्हर्सिटी कोल्हापूर सिलेबसची ऑनलाईन लेक्चर चालू आहे. लक्षात आलं का? आणि तुम्हाला जर पुढची लेक्चर्स पाहिजे असेल तर तुम्ही चॅनल सबस्क्राईब करा, लाईक करा, म्हणजे तुम्हाला सगळे लेक्चर्स पाहायला मिळतील. ओके, तर या ठिकाणी मी थांबतो. धन्यवाद.